Today we are going to talk about metallic bonding and something called network covalent bonding, but I want to review with you quickly the things we've talked about quickly for intermolecular forces of attraction. We've talked about molecular solids so far and how those particles are attracted to each other. Remember, these are nonmetals to nonmetals. We have three categories of intermolecular forces of attraction. For molecular solids, they are dipole to dipole. Do you remember the other two? Hydrogen bonding, good job. And finally, that's right, London dispersion forces, which we call LDFs. These are all molecular solids. They are nonmetals bonded to nonmetals. Of course, we talked about ionic solids earlier in the year. I'm not going to talk too much about them today, but remember that's a metal essentially to a nonmetal. So we could have a positive metal ion to a negative nonmetal ion, and they're held together by an electrostatic force of attraction. It could also be a metal to a polyatomic ion. Once again, a positive to negative attraction. Example of those are pretty simple. Oops, it's not a good little bracket there, but we could have NaCl, MgO, CaCl2. We could even throw in something like CuNO32. So these are all examples of ionic solids. Well, what about metals? What about something just like, I don't know, silver or gold, everyone's favorite, magnesium, zinc, copper, tungsten, osmium, etc. How are those metal atoms stuck to each other in their crystalline lattice? Well, we call that metallic bonding. It turns out that these valence electrons in metal crystals are not just relatively mobile, they are very mobile. They're not attracted to a specific metal ion within the crystalline lattice. And so we use this thing called the electron C model to help us understand what metallic bonding is. The metallic ions are anchored in position sort of like buoys in a mobile sea of valence electrons. Since those valence electrons are not really attached to any particular ion, they can wander through the crystal. And it's that attraction that the positive metal ions, we call them cations, have for these wandering electrons that contribute to what we call the metallic bond. So it's sort of vague and difficult to visualize, but really what you need to know for this class is if you have a metal, an elemental metal, or even an alloy of metals, you need to understand that those would exhibit something called metallic bonding. Their properties are sort of, they're broad. So for example, mercury is a liquid at room temperature, whereas elemental tungsten is the element with the highest melting point of all. Well, they're both held together by metallic bonding, but why would mercury have such a low melting and boiling point and tungsten's be so high? And that's not so easy to explain in this context. So all you need to know for metallic bonding is if you see a metal, you would characterize it as exhibiting metallic bonds. Okay? If you saw nonmetals to nonmetals, you have three choices: dipole to dipole, hydrogen bonding, or LDFs. And if you see a metal to a nonmetal, you classify that as an ionic solid. Now, the last thing I want to mention today would be something called network covalent bonding. So network covalent bonds are literally covalent bonds that exist between the atoms or even molecules in the crystal structure. Now, that is actually pretty profound because metallic bonds are the covalent bonds are the strongest of the bonds between ionic and covalent. Covalent bonds are many times stronger. So these substances have very, very high melting points. It should be MP, melting points, and very, very high boiling points, because their particles are so strongly attracted to each other, because they're literally attracted to each other by covalent bonds. Now, probably the best example will be the allotropes of carbon. Diamond is elemental carbon. So if I were to take a look at a crystal structure for diamond and looked at the carbon atoms, let's pick this one here. Do you notice that that carbon atom that I have highlighted is covalently bonded to 4 other carbon atoms in the crystal structure? This one right here, it's covalently bonded to 4 other carbon atoms in the crystal structure. Well, those covalent bonds are extremely strong. So for this carbon atom to leave, to evaporate, or to melt, even to change that crystal structure, it takes considerable high amounts of energy. So network covalent compounds, once again, have very high melting points and very high boiling points because it's difficult to break down that structure. Graphite is another allotrope of carbon, an elemental form of carbon. So if I take a look at the crystal structure of graphite, I see something pretty cool. Let's take a look at this bottom layer. This carbon atom here, do you see it's covalently bonded to that carbon atom and also covalently bonded to that carbon atom? This carbon atom right here is covalently bonded to this one, and that one right there. So within a layer of graphite, those carbon atoms are held together by covalent bonds. But here's the interesting thing about graphite. Between the layers, they are held together by London dispersion forces. So between the layers, it's a much weaker force of attraction. That's what gives graphite a pretty cool property. Take, for example, your pencil. When you write with a pencil, you're not writing with pencil lead. You're actually writing with graphite. And if you were to drag your pencil point across your paper very, very lightly, you would be leaving layers of graphite behind. Well, how can you leave layers of graphite behind if the carbon atoms are held together by covalent bonds? You can't break those bonds very easily. Well, if you think about it, are you breaking the covalent bonds between carbon atoms when you drag your pencil point across your paper? Or are you breaking these much weaker London dispersion forces? And that's exactly what's happening. When you drag your pencil point across your paper, you are leaving behind layers of graphite because you're breaking those LDFs that are holding those layers together. Another elemental form of carbon is Buckminster fullerene, which was discovered not too long, about 30 years ago actually, in some space dust. We can now synthesize it in laboratories, but if you take a look at this spherical structure, just pick that carbon atom right here, do you notice that it's covalently bonded to 3 other carbon atoms? This one back here is covalently bonded to 3 other carbon atoms. So carbon and allotropes of carbon are held together by these network covalent bonds. Another common substance that's held together by network covalent bonds would be silicon, very, very high melting point and boiling point. Silicon dioxide, sand is its common name. Silicon carbide. Basically, silicon compounds have very high melting and boiling points. Turns out that they're generally held together by these network covalent bonds. So, just to recap, we have several different forces of attraction between atoms or molecules. We have molecular forces of attraction, which of course are dipole to dipole, hydrogen bonding, London dispersion forces. But then we also have these other forces of attraction that we've talked about: ionic bonding or ionic solids, metallic solids, and then finally network covalent solids. In our next video, what we're going to do is we're going to practice these. I'm going to give you examples of each of these, and you're going to have to classify them into one of these 6 categories. I think you'll be able to do it. It's hard at first, but you'll get the hang of it. Okay, that's good enough for today, kiddos. We'll see you soon. Bye-bye.